when we left on Wednesday, we were talking about proton transfers, and not really because proton transfers are interesting from an arrow pushing mechanism point of view. I mean, they're pretty boring. You take some sort of a lone pair, usually, and pull a proton off. But they are among the most common mechanistic steps when you draw multi-step arrow pushing mechanisms for polar chemistry. And so it's important for us to have a handle on proton transfers and which ones are facile and why they should generally be facile. Let's go ahead and take a look at a typical transformation. This is a Fischer esterification where you take some sort of a carboxylic acid, you had an acid, usually hydrochloric acid or sulfuric acid are the common ones, and then an easy to boil solvent, an alcohol solvent, methanol or ethanol are really the only ones that are commonly used. And it's an equilibrium process, and you drive formation of the methyl ester simply by using an excess of the alcohol solvent. You know, what's the acid in this reaction? The reaction is going to start off with protonation of this carbonyl group right here. You're going to start off by protonating the carbonyl. Otherwise, you're never going to get an oxygen nucleophile to attack that. And so what's the acid that protonates the carbonyl? Very hard to know. We touched on this earlier. I can't emphasize this enough that it's hard to know what's the acid. As soon as you put hydrochloric acid in with methanol, you've got an equilibrium situation, and you reach that equilibrium essentially instantaneously. So what is it that's doing the protonation? Let's take a look at that initial equilibrium that you get. We can use that powerful equation I showed you that looks intimidating but is pretty easy to use. All I have to do is look at this equilibrium right here and decide what are the acids on each side of the equation. On this side of the equation, the acid is HCl, and on this side of the equation, the acid is this oxonium ion, this protonated alcohol. Let's go ahead and draw in some pKa values. pKa for HCl is somewhere on the order of about -8, so I'll just go ahead and write that here so I can remember that. pKa is -8. And then over on this other side of the equation, that oxonium ion, the protonated alcohol, has a pKa around -3. I don't think I told you that. I think I told you a protonated ether is -4, protonated water is -2. We're just kind of extrapolating. This is actually a good number. So pKa -8, pKa -3, which of those is the stronger acid? HCl, lower pKa, stronger acid. So the stronger acid is going to drive the equilibrium in this direction. And what's the equilibrium constant for this proton transfer, this acid-base reaction? Well, its equilibrium constant is pretty easy to calculate. I'm not real good with math here, but I can do this. It's KEQ equals 10 to the -3 minus -8, which is equal to 10 to the -5. Now, let me be honest with you. I usually don't use that equation. I just say, okay, 8 minus 3 is 5. And then I just try to work out which side of the equation is favored. I can't keep track of -8 or -5 and +5. I already know which side of the equation is favored. It's going to be 1 to 10 to the 5. And I'm going to write out the zeros there. I now have a much better qualitative picture. Yeah? -3, it's 10 to the... You see, I'm so bad with that. But I know intuitively which side of the equation is favored because I know the stronger acid pushes the equilibrium. Thanks for asking that question. You can see how I'm able to work things out even though I'm not good at the math. I usually just say, okay, 3 and 8, and the difference is 5 orders of magnitude. So immediately we have a qualitative picture. Most of the acid that's floating around in our solution is this protonated alcohol. There's not a whole lot of HCl in there. Less than 1% of the HCl still exists at HCl, but the HCl is more powerful, so you can't know what's putting the proton on the carbonyl. Our initial arrow pushing step for this reaction is going to start with a proton being the carbonyl picking up a proton from some acid, and you have no idea whether it's the HCl that's more powerful or whether it's the protonated methanol that's more abundant. You can't know. So that's why I would encourage you to use HA as a symbolic acid. And you don't claim any knowledge about which of those two species is doing the proton transfer. The rest of this mechanism goes along, and there's more proton transfers here in this mechanism. You know, you add methanol, you generate another protonated species, this oxonium ion, then you pull a lone pair off that oxonium ion, another acid-base proton transfer reaction, and then we have to make a good leaving group out of one of these two OHs. I'll pick the bottom one, it's arbitrary. There's another proton transfer event. And so now we've got a good leaving group, and we can push out that leaving group. And you might wonder, which of these two lone pairs is pushing out that water? I got lone pairs on the methoxy, I got lone pairs on the hydroxy. You know, they're both pushing out the water. You could use either arrow pushing and get to the right one. I'm going to push arrows from this top lone pair here, but you could have pushed the arrows from the methoxy lone pair. You'd come out with the right answer in the end. Won't make any difference. And our last step is yet another proton transfer event here, where we're deprotonating the carbonyl. And as soon as, if you said, I think I know what this A is, suppose you were going to define what the A was, if you just really felt like you had to do that. And I said, oh, my A I'm going to use is going to be this protonated, you can't see that, that's an H up there on that, that's protonated. Boy, that's drawn so poorly, let me just redraw that somewhere. Right, suppose instead of saying HA, I got really specific about my acid that's doing the protonation event there. Suppose I said, oh yeah, that's going to be the methanol, the protonated methanol that's doing the protonation. Now you could even calculate an equilibrium constant for this first step, right? We said that the pK for that oxonium ion is -3, so pK -3 for that oxonium ion. The pK for a protonated carbonyl, well, that's somewhere on the order of about -7, and ester's a little bit different, but it's close enough. -3, -7, which of those is a stronger acid? The protonated carbonyl or the protonated methanol? Protonated carbonyl is a stronger acid. The equilibrium is going to go back this way. And we can do the math here. It's 10 to the fourth in some direction, and I know what direction is favored. You know, it's 10,000 to 1. Just from knowing some cheap pKa's, I get a clearer picture. Wow, only 1 out of every 10,000 carbonyls is protonated at any point in time. Is that plausible for me to do that? Yeah, it's plausible. Is there a lot of the protonated carbonyl or a little? Well, not a lot. Most of the protons are on the methanol solvent. So just by thinking about ratios, you get a more intuitive feel for what's going on in an arrow pushing mechanism or in a reaction mixture. Now, generally, you should consider proton transfers to, even if it's not entirely favorable, most proton transfers to and from heteroatoms are fast. They're fast and reversible. Don't be intimidated about transferring protons to and from heteroatoms. They're fast and reversible. I'm going to give you a simple rule that impresses the heck out of me. Came from the work of Manfred Eigen, measuring superfast proton transfer rates. Whenever you talk about heteroatoms that have some electronegativity, like nitrogen, oxygen, sulfur, including things like chloride, I didn't put that here, acids protonate bases at a diffusion-controlled rate. Proton transfers in the favorable direction, as long as the pK is greater than 3, something is significantly more acidic, when there's an equilibrium going back and forth in this proton transfer event, forwards, backwards, forwards, backwards, one of these two directions is diffusion controlled. And that, in this case, what's the more powerful acid? Let's go ahead and talk about the pKs for these acids. I've got hydronium ion. What's the pK for a hydronium ion? -2. And the pK for a protonated carbonyl? Whoops, let me I'll just write pK -2. What's the pK for the protonated carbonyl? Anybody remember that from the last slide or from that table? Yeah, it's -7. Okay. Which of these is more acidic? pK -7 or pK -2? Yeah, -7. And that pushes the equilibrium back in this direction. That's the favorable direction. And one of those is more acidic by more than 3 orders of magnitude. And so what I can say for certain from that is that this proton transfer in this direction is diffusion controlled. That's a special term, diffusion controlled. What does diffusion controlled mean? It means that every single collision results in a successful proton transfer. Every single molecular collision. Man! You know, most molecules, when you run a reaction, they collide 1 million, 1 billion, 1 trillion times before you finally form a bond. And now I'm telling you this is so fast that every single collision results in a successful proton transfer. That is powerful information. And all I needed to know was a couple of pKas, and I get that information. That should impress you. Now, you're probably saying, well, come on, Dave. What happens if this thing collides with the carbon atom? Is it going to transfer a proton? Okay, so maybe it's 1 out of every 2 collisions, but you still get the idea. Pretty much every single collision is going to result in a successful proton transfer. And that's a big difference between 1 out of every billion collisions transferring a proton. So all I needed to know was those pKas. You might wonder, why do I tell you to memorize those pKas in that table? Because you know a couple of pKas and you can go a long ways to explaining organic chemistry. Now, we look at this same equilibrium process here, and I just told you that this direction is diffusion controlled, but let me be a little bit more specific about what is the rate constant for a diffusion controlled process. Diffusion controlled, it has a number. It depends on the solvent. I'm going to give you a number that's not, it's a Manfred Eigen number when you're using water as the solvent. That makes this number higher than normal. So the numbers that he would give you are somewhere on the order of 10 to the 11th per molar per second. And the reason why it's about 100 times faster, about 2 orders of magnitude bigger than normal, is because water is the actual solvent for the reaction. So it changes the equilibrium kinetics. If you know the rate constant in one direction, so that's 10 to the 11th per molar per second is diffusion control. Let me write this down here. That's the diffusion controlled rate when one of the acids or bases is the solvent. If I know the pKas in both directions, let me come back over here, pK minus 2. And over here it's minus 7. And KEQ is equal to 10 to the 5th. No, 10 to the minus 5 here. Am I getting that right? Check me on that if I'm screwing that up. 10 to the minus 5. 10 to the minus 5. If you know KEQ, here's a powerful piece of information that you probably haven't used since you were an undergraduate. The equilibrium constant can be interpreted in concentrations, but you can also interpret the equilibrium constant in terms of rate constants. If I use a rate constant K1 in the forward direction and K minus 1 for the rate constant in the backward direction, the equilibrium constant can be defined as the ratio between the forward rate and the backward rate constant. Forward rate and that's K minus 1 on the bottom. K minus 1. Now, I know this. I know this number. It was like minus 7 minus negative 2. I know KEQ. I can calculate that. And I know this because it's the diffusion controlled rate. That means I can even, if I wanted to, I could calculate the backward rate constant. I can calculate that. That's easy to calculate. Now, I don't think it would help you to know that the forward rate is, I'll just write calculate. Wow, that's a small, you can't even read that. It says calculate that. You can calculate that. You would figure out by using that simple equation, if you wanted to, we're not really doing that in this class, that the forward rate constant is 10 to the 6th per molar per second. Man, all I needed to know was a couple of pKas, and I can figure all this stuff out. Now, this is going a little too far. I'm not going to ask you to calculate rate constants, but I do expect you to know that proton transfers from acids to bases are diffusion controlled in the favorable direction, as long as you're transferring to and from heteroatoms. Transferring to carbon, this rule breaks down. It's not, hydrogen bonding is the first step in proton transfers, and alkyl CHs aren't good at hydrogen bonding. So, but we're going to have a lot of proton transfers in our mechanisms in this class where we transfer protons to and from O plus, O, N, N plus, chloride minus, things like that. Okay, so proton transfers, we'll do a lot of that. Memorize the pKs in that table. Be ready to think about, oh yeah, there's 1,000 times more of this, or maybe the ratio is 10 million to 1. You'll hear me say that kind of stuff while I'm flying through a mechanism, and you'll wonder, where did he get that? I'm fast at doing those kinds of ratios. Okay, we're going to switch big-time gears. Finally, we're going to start talking about carbon reacting. Well, that's what we really want to do. It may seem like we're getting a slow start, but things are going to accelerate. So we're going to talk about the reactions of carbocations. So empty p orbitals. And this is the way you start talking about reactions in most introductory organic classes. They start telling you about SN1 reactions, things pop off, or versus SN2 reactions, forming carbocations. Is that okay to form a carbocation? Should I expect things to donate into carbocations? What kinds of things stabilize carbocations? We're going to address all of those questions now. But before I start on that, I got to resolve like some real complexity and some misunderstanding. So let's talk about cations. Right? You'll see in any introductory organic chemistry class 3 common classes of cations. You're going to see carbocations in SN1 reactions. From the time you were taking general chemistry, you were talking about ammonium ions and pH and equilibrium processes. And we've seen H3, I remember learning about H3O plus when I was in high school. We talked about ion product constants and hydroxide, hydronium equilibria. You know, I've got 3 different arrow pushing events here. You know from taking an introductory organic chemistry class that nucleophiles just love to attack carbocations. They just love that. That's a super facile process. What about these other processes? Which of these processes, these nucleophilic attacks, are good? Well, attacking the carbocation is good. I'm going to say that's good. This is good. What about attacking the ammonium? There's no way. There's no freaking way you would attack that N+. What about attacking the hydronium oxygen? Well, you knew since you were in high school that that's absolutely ridiculous. You know, how come there's no generalization here? These are all second row atoms, and it seems like they forgot to tell you something. And you may think, oh, that's crazy. How come nobody's ever going to make that mistake? I see it all the time when I'm teaching classes that people attack the O+ of a protonated carbonyl. Right? How come there's not some obvious way to distinguish the reactivity here? How come sometimes you attack the thing with the plus? Right? Well, generally, don't attack charges. Charges don't form bonds. Electrons form bonds. Let's talk about this. The reason why this is so complex is there's 2 completely different classes of cations. 2 different classes of cations. And if you don't distinguish them, you're going to be forever, ever confused in organic chemistry. So before we start a lecture on carbocations, let's talk about which family of cations we are talking about. So there are 2 families of cations. One family of cations are called the eniums, and the other family of cations are called the oniums. They have completely different reactivity and completely different stability. So this carbocation that you've been drawing the whole time in organic chemistry is called a carbonium ion. You've been calling it a carbocation, but when you called it a carbocation, you didn't distinguish between whether you were talking about a carbonium ion or a carbonium ion. Those are both carbocations, and they have completely different reactivity. Now, there's another enium ion other than a carbonium ion. I'm not sure whether you call it a nitrenium or an aminium. It is so rare that nobody makes it, nobody talks about it, nobody forms it. I couldn't find the correct way to name that because it's so unusual. And if you try making an HO plus with 6 electrons on oxygen, there's no way. It's just not conceivable. I don't know whether that's called an oxenium or a I don't know the name of that. So rare and so crazy. It's hard enough to make a carbonium ion, and carbon is not very electronegative. There's no way you're going to make an aminium or oxenium ion. There's no way. So you're never going to see these as a result. That's why we've never talked about those. Let me use a different pen color there, but no, we just don't make these. No, we don't. You're never going to see this, so just blot it out of your mind. Now, when we talk about onium ions, we've all seen a hydronium ion. Hydronium is a specific variation of oxonium. We've all seen an ammonium ion. You've all seen that. Ammonium chloride, HCl and ammonia makes ammonium ions. But how many of you have worked with, in mechanisms, drawn mechanisms involving carbonium ions? You might say, that's crazy. Somebody told me you can't have 5 bonds to carbon. Sure you can. You just can't have 10 electrons. Notice the positive charge over here on that carbon atom? That's what makes it okay to have those 5 bonds. You might say, well, I'm never going to see anything like that. Sure. You drive down the 405 freeway past this Chevron plant or whatever. They're taking long gasoline molecules and cracking them into short molecules by putting protons onto alkanes. Alkanes will fragment apart to make short gasoline molecules. It goes on everywhere. Super common chemistry, and now very easy now that we have a class of reagents called superacids. Yeah.
How would like orbital hybridization be for like the carbonium?
We don't have time to talk about that, but you know, if you just take methane and you add a superacid to this, we don't have good ways to push the arrows for this. So if I take a superacid and I put it in there, and right, the only thing you've got are these CH bonds. I'm going to use a dashed line here. And the only representation we can draw is something like this, right? The carbon still has 8 electrons. A CH bond definitely attacked that proton in an acid-base reaction. And this is the best representation of the carbonium ion that we've got. And as long as we keep that positive charge on the carbon, we can do arrow pushing with that, and we won't end up with wrong results. It's the sigma orbital on methane or on an alkane that would attack the proton in a superacid reaction. Yeah, I wish we had time we could have a whole lecture on the reactivity of carbonium ions. We don't have time for that. Okay, so this is why things are so confusing. People have talked about the things that are common, and the things that are common are carbenium ions, ammonium ions, and oxonium ions, and they belong to different families of these cations. So I will try to use the word carbenium ion in this class. I will try to avoid the use of the word carbocation, because carbocation doesn't tell you whether I'm talking about carbonium ions or carbenium ions. But I recognize that this carbenium ion name is unfamiliar to you, and it may confuse you. But if you're trying to be specific and convey information, carbenium is the correct way to describe those carbocations that you've been working with since you took introductory organic chemistry. Okay, so you know, this course is all about reactions, and which reactions are good and which reactions are bad. You know, empty p orbitals on carbon are so reactive; they are just crazy reactive. Anything can add to that empty p orbital on carbon. Right? I guess it depends on the stability, but you'll find examples of just about anything you want adding to carbenium ions, right? Nucleophile lone pairs can add to carbenium ions. Chloride, water, ammonia, if you could get it in there in the midst of... So there's nothing, I hope, unusual about this idea that a nucleophile with a lone pair, that non-bonding lone pairs can add to carbenium ions. That should not be surprising to anybody. That's common in SN1 reactions. You make carbenium ions, you attack them with lone pairs. Standard stuff. Pi bonds can add to carbenium ions. You already know that. If you've taken any course in organic chemistry, then you should already know that pi bonds can add to carbenium ions. That's the basis of the Friedel-Crafts alkylation. You've seen that before. If a benzene ring double bond can do it, an alkene could do it even easier. You don't want to do Friedel-Crafts reactions if there's alkenes floating around, because the alkenes will also add to your carbenium ions. And in this case, the intermediate you get is another type of carbenium ion, very special one called an arenium ion. We're not going to go through that whole mechanism right here, but hopefully you've seen bunches of benzene rings and arene rings attacking carbenium ions. Hopefully you've seen that before. Sigma bonds can attack carbocations, carbenium ions. Now, this may not be so familiar to you. If I took a primary carbocation, that's just insanely reactive, a primary carbocation. We just don't talk about that very much. If you did, you'd start to see hydride transfers occurring. You'd start to see processes like this. This turns out to give you another primary carbocation with the same stability, but right, you still have to worry about what's uphill and what's downhill. Right, this would be equilibrium ratio of 1, but yeah, you can use sigma bonds to attack carbenium ions. You've seen this before. You've seen this a lot, maybe. This is the basis of a 1-2 shift, either an alkyl or a hydrido shift. Right, that's a sigma bond attacking a carbenium ion. Lone pairs can attack carbenium ions easily. Pi bonds can attack carbenium ions easily. Sigma bonds, not so easily unless you've got fantastic orbital overlap like this, where things are really close in space all the time and can't get away. That makes it a really facile process. Okay, I'm not really that excited about talking about attack on carbenium ions because it's just such easy pickings. Yeah, anything can pretty much add to a carbenium ion if it's not stabilized. What we're going to be interested in this lecture or this topic is we're going to be talking about, okay, well, what if you stabilize that carbenium ion? Now it's not so easy. Now it might get a little bit more choosy about what it reacts with. And that's what we got to think about. Are we even going to be able to form a carbenium ion? Well, that depends on how stable it is. So we're going to spend quite a bit of time talking about, how stable are carbenium ions and what is it that determines whether you can form them. So I'm going to take you back to introductory organic chemistry, and let's go ahead and think about the most common reaction involving a carbenium ion, which is an SN1 reaction. Suppose I take some sort of a reactant like T-butyl chloride, and I just want to ionize that off that chloride bond, or bromide, or iodide, or some sort of thing. There's going to be this process where you break the bond, and when we do that, we're going to generate a carbenium ion out of that. You've probably called it a T-butyl carbocation, but that's just one variation. So I'm going to draw an energy diagram so it's clear that carbenium ions are high in energy. They're way high in energy. 6 electrons, that's no good. You want 8 electrons on carbon, so that's going to be high in energy. And if I draw out that carbenium ion, I would draw it as planar. Carbenium ions are planar. They have a positive charge somewhere. That's not really the big issue. The big issue is that it's only got 6 electrons. And I could sketch out the orbitals here. It's like a p-type orbital above and below. I'll kind of shade one of those 2 orbitals. And then somewhere floating around, I'd have that X minus leaving group, X minus floating around, and then there'd be the nucleophile just sitting there doing something, waiting to do something. If this is I'm trying to draw a reaction coordinate diagram, and I'm not sure if this is the first reaction coordinate diagram that I've drawn in this class, but you'll notice some things going on with a reaction coordinate diagram. So first off, we've been doing a lot of MO diagrams where there's no horizontal axis. Now there's a horizontal axis here. What is that thing? They usually say reaction coordinate. Now what does that mean? Usually in this case it means the distance between the carbon and the X. As the X floats away and gets farther and farther away, what's happening to the energy of the system. But sometimes it's not a simple one-dimensional variable like that. It's for more complex reactions. The other thing that's different is I'm talking about delta G in kcals per mole, not MO energies in electron volts. Kcals per mole, I can convert into factors of 10. That's useful. So what's happening here? So as the X gets farther and farther away till it finally dissociates to make a carbocation, I have to go through some transition state. And then the nucleophile can attack that so easily, there's not much of a transition state going in that direction. Anything can attack a carbenium ion. Going backwards, going forwards, that's easy. The barrier is low. Anything can do that. So this would be a reaction coordinate diagram for an SN1 process. And if I've got 2 different species that could attack, right, and one attacks with a transition state 1.4 kcals per mole lower in energy than the other, you could calculate the rate constants going in each direction. 1.4 kcals, that's a factor of 10 in rates going in one direction versus the other. So you can use kcals per mole with reaction coordinate diagrams. You can't use kcals per mole or convert those to ratios with MO diagrams. That's not really the way we would think about that. Okay, so you should know that you can ionize good leaving groups and make stable carbocations and then come back in and attack them. Now because carbocations, carbenium ions are planar, this carbenium ion that I've got here is planar, and that means that we can attack either the top or the bottom. So if I look at this case down below here, where I'm doing in acid conditions, I'm doing SN1 type reaction. So what is one clue that this might be an SN1 process? Well, my clue is down at the bottom here. They're doing this in a polar solvent, acetic acid. When people want to make carbocations, way back in the 60s, this is like every paper that was published was, let's make a carbocation and publish another paper. And every time they used acetic acid as the solvent for that reaction because it's polar. And you want polar solvents for SN1 reactions. Water is polar. Polar solvents are good. Why should that be good? Well, because you're separating charges. I'm not going to go back and review Coulomb's law with you, but Coulomb's law tells you it's hard to separate charges. You want the high dielectric constant in order to be able to separate charges, and polar solvents have a high dielectric constant. It makes it easier to pull charges apart. You could calculate the energy and convert it to kcals per mole if you wanted for how hard it is to separate a leaving group to a non-bonding distance. But this polar solvent acetic acid helps. The lithium also can coordinate to the OH in addition to protons. I'm not going to draw out the carbonium ion intermediate. I'm just going to ask you, what's the product? What's the configuration of the bromide product you get in this reaction? I've got two possible products here. So one possible product would be this. Or I do that with inversion. That certainly would be true if this were an SN2 reaction. But remember, the carbonium ion intermediate that I generate, when I protonate this, let's go ahead and draw some of that stuff here. Here's what would happen. And if you coordinated lithium, I wouldn't say you were wrong. You know, they're using lithium. You ionize that oxonium group off to make a carbonium ion, and then the bromide comes back in and attacks. But you'll get an equal mixture in this case of the two enantiomers. It would be a racemic product because it's equally likely that the bromide could attack from the bottom face or the top face of that carbonium ion. So just remember, carbonium ions are planar, and its nucleophiles have the potential to attack from the top face or the bottom face. And unless there's something that blocks one face, you'll get equal amounts of attack. And there's nothing different about the two faces of the carbonium ion intermediate that would be involved in this reaction. So this is a two-step process like I've shown in the reaction coordinate diagram above. Okay, what kinds of leaving groups can do that? What kinds of leaving groups can you just pop off? You start with a neutral compound and then suddenly you ionize it to give a plus and a minus charge. Here are some of the common leaving groups. I think you've all seen very commonly these leaving groups in any introductory organic chemistry class. Iodides, bromides, and chlorides are the most common leaving groups they teach you in an introductory class. They were certainly common 120 years ago when some of this chemistry started to become popular. And those can all ionize and pop off. You should have also been introduced to something called a tosylate leaving group. You take alcohols and you treat them with tosyl chloride and you generate this leaving group called a tosylate. So it's easy to make alcohols into tosylate leaving groups. Now we have an abbreviation for that leaving group here. So when you make that leaving group, we would call that abbreviate that as OTS, and this initial alkyl substrate would be called, you could abbreviate by saying ROTS. There's a tosylate there, and the bond is ready to break. So this process of having some sort of a group break and give the electrons here would end up giving you a tosylate leaving group that floats around. I'll often abbreviate it by drawing something like this, OTS, or TSO minus, or OTS with a minus on the O. We're going to draw that in this class. And I expect you to know it's a sulfonate, kind of like sulfuric acid, but it's an alkane sulfonate. There's a very simple alkane sulfonate that you've seen, or at least we teach it at UC Irvine, that looks very similar with a methyl group on there. We call this a mesylate leaving group, and it's got its own abbreviation, R bond OMS. And those bonds can leave. You draw the arrow pushing like this, just like the tosylate. They're not as common as toluene sulfonate. The tosylate's much more common. And if the leaving group comes off, you could draw it like this. And if you needed to use those lone pairs, you could draw lone pairs on the oxygens just like that and use it for arrow pushing. When you draw it like that, I expect you to know the chemical structure, the Lewis structure for that leaving group. Even if you don't draw the whole mesylate O, if you draw it as MSO minus, then I still expect you to know what the structure is. So you could also draw it like this in this direction, and that's fine. It won't make any difference. We understand. Same with the tosylate, TSO minus. That's good. Now, when you really want to get down to business, right, you don't mess around with tosylate or mesylate. You make something called a trifluoromethane sulfonate or triflate. Man, this is crazy. Holy cow. Triflate. That is a reactive leaving group. I'll give you some numbers in a second here, but when you want to really make a leaving group, you use a triflate. And the counterion that you get when you do this ionization process, when you ionize off these types of leaving groups, this triflate leaving group is super unreactive. Right? You might think, oh, it's got O minus. It's as reactive as hydroxide anion. Not even close. You're going to have a hard time getting triflate even to pick up a proton. Right? Triflate anion is an amazing leaving group. Let me go ahead and give you some numbers here. I'll try to put some numbers in terms of leaving group ability. I'm not sure what pen color to use here because I've got so much stuff written here. Triflate versus, notice here that I've said that tosylate and mesylate have about comparable reactivity. There's nothing that interesting. If you made a tosylate leaving group in this class, a mesylate would have about the same reactivity. We're not going to worry about any differences in reactivity there. The difference is between triflate and tosylate. That's a massive difference. 10,000 times better as a leaving group. That's a factor of 10 to the 4. Triflate is 10 to the 4th better, 10,000 times faster as a leaving group than tosylate. What if you could do your homework 10 to the 4th times faster? Wow, that's a substantial difference. And when we talk about the difference between tosylate and, for example, alkyl iodides, well, the tosylate's 10 to the 3rd faster than an iodide as a leaving group if you're doing ionization reactions. Now, iodide is better than bromide, is better than chloride. That's bond length there again, right? You know that from bond length. I'm not going to give you numbers for those differences. But if you take an alkyl chloride and then compare it to just a regular ester, not a sulfonate ester, but a carboxylic acid ester, right? This difference here, carboxylic acid esters, they're lousy leaving groups. I'm showing you a special one that has a nitro group on the other side of a benzene ring, on the other side of a benzoate ester. And if you want a lousy leaving group, not sure why you would ever want a lousy leaving group, but if you wanted a lousy leaving group, back in the 60s they sometimes used this, a paranitrobenzoate. Maybe in some of the old literature it might have been abbreviated PNBO minus, but let's just be honest with ourselves, that's lousy. And we're not going to do a lot of leaving group chemistry with lousy leaving groups in this class. If you're going to use just a neutral carboxylate as an anionic leaving group, you might want to think twice about having a neutral carboxylate ionize off. Okay, so these are some of the common leaving groups we're going to see in our mechanisms in this class. If you're trying to make carbocations, and if you really want to make a carbocation, you'll probably be using a polar solvent to do that. Okay, so how do we make stable or unstable carbocations, carbenium ions? Well, let's go ahead and talk about hybridization. We've said that hybridization is super important in this class. So if you want to make an empty orbital, we know how to rank orbitals based on hybridization and their energy. And so I've just kind of sketched out some orbitals based on the hybridization of the carbon atom. So I think we all know that p orbitals have this kind of bilobal shape where, if you did have a pair of electrons, they would spend half their time in the right shaded portion and the other half of the time in their left shaded portion. Now, if I add s character and make an sp3 orbital, and if it were empty, that would suck, right? That would be, you want your lower energy orbitals to be filled, not empty. And the more s character you add, the lower in energy that is, and the more it wants to be filled. When you finally get down to an sp hybridized orbital, man, that does not want to be empty. Things with sp hybridization want to be filled. That's going to be a crappy-ass carbocation, carbenium ion. You can see hates, just despises that, hates being empty. You do not want to be generating empty sp hybridized orbitals. Hates being empty. If you're going to make an empty orbital, make it an empty p orbital. Right? You don't want those. You want to put electrons into lower energy orbitals, not empty them out. So if I give you something like this diazonium ion, this arene diazonium ion, don't do this. Well, I'm trying to draw dashed lines. It's not working very well. I'm saying don't do this. That's crazy. Because if you do that, you're going to be stuck with an sp2 hybridized carbenium ion. Right? You don't want sp2 hybridized carbenium ions. You want p hybridized carbenium ions. Arene diazoniums are reactive. They react on the end of the nitrogen atom. That's how they react. And if you heated this up and made it do something, the diazonium would come off somehow, but it's not through an SN1 ionization process. We're not going to talk about what these do, but it's not going to be through a simple SN1 process under normal laboratory terrestrial conditions. Now, is it impossible to make something like an alkenyl anion or a cation? No, it's not. We do this all the time. So when you take alkynes and you protonate them, there is no problem protonating alkynes. There's no problem doing this. But when you protonate an alkyne to make a carbenium ion, it is not bent like this thing here. It doesn't look like this, because that would be crazy. The shape of that carbenium ion is linear, like this. That's a regular p orbital right there. It's linear. If it were bent, you'd be stuck in this situation over here, and that would be a big-time loser situation. And so it stays linear just like it was in the starting material, because that means the empty orbital is p hybridized. You don't want to have S character in your empty orbitals. That's not a good situation. And I gave you these methyl anion affinities, and one of the most reactive functional groups conceivable would be this sp hybridized situation over here. This was an acetylide cation was much more reactive than any other type of carbocation. I couldn't even fit it onto the diagram. There was this like discontinuity in the diagram. Never heard of that. Maybe if you went into outer space and you're in a vacuum, you could make that, but nothing on the planet Earth will ever have an sp hybridized carbenium ion. That's just insane. Now, once you start to, back in the 60s, people were all excited about making carbenium ions through ionization reactions. Put things in acetic acid, heat them till something happens, try to look at what kinds of carbenium ions you can make. So here's some examples of alkyl chlorides. They're all trisubstituted. They're all tertiary alkyl chlorides. You'd think they would all react at the same rates. They don't react at anything like the same rates. You can't form equally stable carbenium ions out of these. Let's go ahead and take a look at the relative rates for these ionizations. I took the time to look these up. So if I looked at the relative rate constants, I don't care about the absolute rate constants measured in per molar per second units. I'm just going to write relative rates. 10 times faster, 10 times slower, 3 times faster. What's the difference in rates for these ionization reactions? They all make carbocations if you ionize like that. The one that I'm going to use as the base case here is going to be this one. I'm going to assign that a relative rate of 1. Are the other ones faster or slower than this? It's a bicyclo 2220 system. You don't need to know the actual name. For that tertiary alkyl bromide in the middle, this one over here is 100 times faster. This is called an adamantyl ring system. So adamantyl bromide ionizes 100 times faster. They both give tertiary carbocations, carbenium ions, but this adamantyl system is 100 times faster. And the one with no cage structure, I couldn't even, that's 1,000 times faster. And this one with this simple acyclic structure that can become easily planar, that's so fast I couldn't find a relative rate for that. It's greater than 1,000 times faster. It's more reactive than any of these others. This one over here on the far end that is more reactive can easily become planar. Planar, no problem, no hindrance to becoming planar. All these others, because of that cage structure, can't easily become planar. And so it's hard to make an empty orbital when you can't become planar. I get back over to here where I've tied up the bonds in all these rings. Man, that just cannot planarize. Look what you're stuck with. All those tight bond angles there, that can't be simple p hybridization of that empty orbital. Right? We've got a number for this. It's 10 to the minus 7 fast relative rate. Man, you don't want to be making empty sp3 hybridized orbitals. That's just crazy. So it can't planarize. That can't become, right, not planar. It's pyramidal, and that sucks. And that being pyramidal means more. There's S character in there. That's AL at the end of that. That's whatever. It looks like 2 Ds. Pyramidal. Pyramidal. So suck. Big suck time carbenium ion there. So hybridization matters. S character, P character. P character, when you talk about occupied orbitals, when they've got electrons in them, pairs of electrons that have P character are nucleophilic, but you don't want to have empty orbitals that have S character in them. Okay, let's take a look at some neutral leaving groups. Right, when you do this type of an SN1 ionization reaction that I'm showing over here, you go through an intermediate, like this oxonium ion, you protonate the water. I'm not going to show that step. HCl can add a proton to the OH. Hope you know that chemistry from your introductory organic chemistry class. You have this oxonium ion leaving group, and then that leaves, and it'll make a carbonium ion. And in this case, your leaving group is charged. Your leaving group has a positive, your starting material has a positive charge, your leaving group, or the carbocation has a positive charge. People still tend to use polar solvents for these reactions, even though your starting materials are charged, have a positive, and your product mix, the intermediates have a positive charge. Let's take a look at some groups that start off as, I don't know why I included a diazonium ion in here. It's not exact. You start off with an amine, and in the reaction mixture make a diazonium, but I'm trying to put it on this list here of leaving groups. Maybe I should have put it on that other list of leaving groups. Oh, I know why, because all of these are positively charged. So if you take an OH group, that's lousy. Hydroxide anions don't act as leaving groups in SN1 reactions. We'll see them act as leaving groups in other cases. But you stick a proton in there, and suddenly that starts to look like a good leaving group. If I take an ester, and I forgot to draw the oxygen there, fix that to put this oxygen, there should be an oxygen. Esters can act as leaving groups, but you got to protonate those. You don't want a situation like that nitrobenzoate anion. What you want to do is stick a proton on the ester so that it can act as a leaving group. And critically, where do you put that proton? Here's where you put the proton. You put it here on the carbonyl. Do not ever, ever, ever put the proton on this carboxyl oxygen. You put it on the carbonyl oxygen right there. Protonate the carbonyl, not the carboxyl. If you drew a resonance structure, it would be immediately obvious that there's partial positive character on that carboxyl oxygen if you draw resonance structures. And there's partial negative character over here on this carboxyl. And when you do that, it's just as easy to generate a carboxylic acid leaving group with arrow pushing. Watch this. I'll take the arrows, add there, give the electrons to the O+, and that generates the same carboxylic acid leaving group as if you put the proton on the other oxygen. So this is the way you make carboxylic acids act as leaving groups. You protonate the carbonyl. And you don't need to worry about that for a protonated ether or protonated OH. Those act as leaving groups. Diazonium is the best of all of these, right, that gives nitrogen gas as the leaving group. That's the best neutral leaving group that you'll have in this class, is nitrogen gas as a leaving group. Sometimes, we're going to see in this course, that we don't always use protons. Sometimes we want to be a little bit more choosy and more selective, and we transfer silo groups. It kind of acts like a fat proton is something I've heard people call this. And it changes that carboxylate into a leaving group. And you end up with this fabulous oxygen-silicon bond. Man, oxygen loves silicon. And so if we draw out the arrow pushing for that, it would look like this, just like before. And it gives a silyl ester with that magnificent oxygen-silicon bond. Look at that bond there. Oh, man, it's awesome. Yeah? You can't assign p character until you draw resonance structures. And so when I draw the resonance structures for any kind of an ester, it looks like this. There's negative character on the carbonyl, and there's positive character over here on the carboxyl oxygen. You would never put a proton on here. It just is not. So you have to consider resonance before you assign the hybridization. So always protonate here. This is the site of protonation. And the site where you had silicon, site where you had Lewis acids. Okay, and the last type of leaving group that will be very common, mostly in SN1, but you'll see this used also in SN2 type processes, not with tertiary oxygens. And that's this phosphonium oxide species here. And you can break this bond. There's two ways to do it. You give the electrons to O and have P plus O minus, or you can make a PO double bond, super stable there. Okay, that's the end of where we're going to cover for today. So you're going to see a lot of these leaving groups used to make carbocations, to make carbonium ions, to be more specifically. Get ready to draw a bunch of arrow pushing where you're breaking bonds and making super crazy reactive carbonium ions. Yes, I got a question.
Quick question. So when in like the esters, like when the oxygen leaves, is that all one step, or is it protonation first and then the single bond?
All of this is one step.